This video is brought to you by mywayteaching.com.
And here R is universal gas constant. Okay, so we know for 1 mole of gas, we already studied the equation, that is delta Q is equal to delta U plus P into delta V. If delta Q is absorbed at constant volume, in that particular case we can take delta V is equal to 0, isn't it? So Cv is equal to delta Q by delta T at constant volume, which is equal to delta U by delta T at constant volume. So it is delta U by delta T. So where the subscript V is dropped in the last step because internal energy of an ideal gas depends only on temperature. On the other hand, delta Q is absorbed at constant pressure. When we consider at constant pressure, in that particular case, we can write Cp is equal to delta Q by delta T with the subscript P, that is delta U by delta T plus P delta V by delta T. The subscript P can be dropped from the first term since internal energy of an ideal gas depends only on temperature. So now for a mole of an ideal gas, PV is equal to RT, which gives P delta V by delta T at constant pressure is equal to R. So here it gives the relation. Now let us study thermodynamic state variables and equation of state. Okay. Every equilibrium state of a thermodynamic system is completely described by specific values of some macroscopic variables. We already know about these macroscopic variables. They are also called as state variables. So whatever, but you take any equilibrium state of a thermodynamic system, that state can be completely described by the values of these macroscopic variables, which are also called as state variables. For example, you just consider an equilibrium state of a gas is completely specified by the values of pressure, volume, temperature and mass, isn't it? That is a better example. On the other hand, a thermodynamic system is not always in equilibrium. For example, a gas allowed to expand freely against vacuum is not an equilibrium state. As you can see in the figure, see a gas here, it is allowed to expand in a vacuum, and this is not the equilibrium state, because during the rapid expansion pressure of the gas may not be uniform throughout. Similarly, a mixture of gases, if you take, when they undergo an explosive chemical reaction, mixture of gases, a mixture of petrol vapor and an air, when they ignite, they produce a spark. That is also not an equilibrium state because their temperature and pressure are not uniform, as you can see in this particular case. So eventually the gas attains a uniform temperature and pressure and comes to thermal and mechanical equilibrium with its surroundings with the exchange of heat energy. Okay. In short, we can say thermodynamic state variables describe equilibrium states of systems. The various state variables are not necessarily independent. The connection between those state variables is called as equation of state, which is very important. Connection between the state variables, it is called as equation of state. That is, PV is equal to mu RT. For a fixed amount of gas given mu, there are thus only two independent variables. One is P and the other one is V or T. One is P and V and the other one is T and V. The pressure volume curve for a fixed temperature is called as isotherm. Okay, the pressure volume curve for a fixed temperature. This is called as isotherm. Okay, isotherm. And the thermodynamic state variables are of two kinds. Okay, in these thermodynamic state variables, we have two types. One is extensive and the other one is intensive. Extensive variables indicate size of the system, whereas intensive variables such as pressure and temperature do not. To decide which variable is extensive and which is intensive, you just think of a relevant system which is in equilibrium and imagine that it is divided into two equal parts. The variables that remain unchanged for each part are intensive, and the variables whose values get halved in each part are extensive. It is easily seen, for example, the internal energy, the volume, the mass are extensive variables because they divide. Now when we divide two parts, when we divide the system into two parts, these things will become half: internal energy, volume and total mass. Whereas pressure, temperature and density, they are intensive variables because they will not change if you divide the system. So it is a good practice to check the consistency of thermodynamic equations using this classification of variables. For example, in the equation, that is delta Q is equal to delta U plus P into delta V. The quantities on both sides are extensive. The product of an intensive variable like P and an extensive quantity, that is delta V, it will also become extensive. Okay. This table, it lists the measured specific and molar heat capacities of solids at atmospheric pressure and even at ordinary room temperature. Okay, you can see here the substances like aluminium, carbon, copper, lead, silver, tungsten, and specific heat as well as molar specific, the capacities is given in this particular table. Okay. See, which means the predictions of specific heats of gases generally agree with the experiment. We can use the same law, that is equipartition of energy, that we use to predict the molar specific heat capacities of solids, isn't it? You just consider a solid of n atoms, each vibrating about its mean position. An oscillator in one dimension has average energy of 2 into 1 by 2 kb t. That is equal to what? Kb into t. That is what they're telling is an average, the solid having n atoms each vibrating about its mean position and oscillated in one dimension has average velocity of 2 into 1 by 2 kb into t, that is equal to kb into t. In three dimensions, the average energy is 3 kb into t. For a mole of a solid, then the total energy is given by 3 kb into t in three dimensions, which is multiplied with the number of atoms, that is Na. At constant pressure, we know that is delta Q is equal to delta U plus P into delta V. Since for a solid delta V is negligible, we can consider C is equal to delta Q by delta T, or in other words, that is equal to delta U by delta T, that is 3R. So as you can see in this table, the experimentally measured values which generally agrees with the predicted values 3R at ordinary temperatures. Okay, the agreement is known to break down at low temperatures. At ordinary temperatures, that is true. Now let us study specific heat capacity of water. The old unit of heat was calorie, isn't it? 1 calorie was earlier defined to be the amount of heat which is required to raise the temperature of 1 gram of water to by 1 degree Celsius. This is what the calorie meant. With more precise measurements, it was found that the specific heat of water varies slightly with temperature. You can see in this figure, it shows this variation in the temperature range of 0 to 100 degrees Celsius. Okay, the specific heat capacity, it varies with the temperature. Okay, from 0 to 100 degree Celsius here that we have taken in this particular graph. For a precise definition of calorie, it was therefore necessary to specify the unit, that is temperature interval. 1 calorie is defined to be the amount of heat, okay, which is required to raise the temperature of 1 gram of water from 14.5 degrees Celsius to 15.5. Since heat is just a form of energy, it is preferable to use the unit, that is joule. SI unit for the specific capacity of water. In SI units, the specific heat capacity of water, we already know this, that is 4186 joule per kg per Kelvin. So the so-called mechanical equivalent of heat defined as the amount of work needed to produce 1 calorie of heat is in fact just a conversion factor between two different units of energy. Okay, calorie to joule. See, in SI units, we use the unit joule for heat, work, or any other form of energy. The term mechanical equivalent is now superfluous and need not be used. It is just two different units, so we no need to worry about it much. See, the specific heat capacity depends on the process or conditions under which heat capacity transfer takes place. Okay, so this specific heat capacity, it depends on the process, okay, or the conditions under which heat capacity transfer takes place. For gases, for example, we can define two specific heats: specific heat capacity at constant volume and specific heat capacity at constant pressure. For ideal gas, we have very simple relation, that is Cp minus Cv is equal to R, where Cp molar specific heat capacities of an ideal gas at constant pressure. Of an ideal gas